Alright.
En ik word geacht hierin te spreken.
Ja.
Alright, welcome everybody to the new edition of the BètaBreak. Welcome also to the people who are watching us online. It's the first time that we are live streaming, so please feel free to interact with us through the comment section. We will monitor those questions as well.
Yeah, so I have comments right here, so anybody who's live right now could just ask us questions and I will answer them immediately.
So my name is Frank and this is Linde. And today our topic is extraterrestrial life, also known as alien life. And we invited two amazing guests to talk about the subject with us. We've got Vincent Icke and René de Metz. In a bit they'll introduce themselves, and after that Vincent will give a short introduction to the subject, and René will have an addition to that. After that, we will start with the talk. We will first talk about life. What is life? What do we define as life? And we'll continue with talking about how are we currently searching for this life. And we'll finish with some more social questions, such as what should we do when we encounter life, or intelligent life even, and things like who owns space. So at any point during the discussion, feel free to interrupt us, ask questions. And then now I'll give the word to René to introduce himself.
Good afternoon. My name is René de Metz. It's not switched on.
Oh yeah,
Meer zo, op deze manier.
Yeah?
Is that the right method?
Even closer, I think.
Even closer
Yes.
than that. I will continue like this. My name is René de Metz. I'm a biologist. I'm born and raised in Amsterdam. I've been studying here at this place before it was called a science center. And I have been studying and working here till 1990. And then I made a transfer. I started working in the space world at ESTEC in Noordwijk, the technological center of ESA, the European Space Agency in Noordwijk. And since that time, 30 years long, I've been working as what they call a science coordinator. That means I was the interface person between the biologists who wanted to run an experiment in space and the rocket scientists. And I have to explain to both parties what they wanted and how, what the constraints were, what the test scenario was, everything. I'm retired by now, since a couple of months. So I have been working for ESA, and now I'm on my own. I closed the doors, and I'm ready to join meetings like this one. Good.
Okay, thank you very much. Vincent?
Good afternoon. Thank you very much for your kind invitation. My name is Vincent Icke. I am a professor of theoretical astrophysics and I'm a visual artist. In my research, I focus on basically two things, one that is publishable and one that is not, at least not for the moment. The publishable part is what you call radiation hydrodynamics. In other words, how does stuff move in the universe under the influence of gravity and radiation? That's relevant to, for instance, the formation of galaxies, the formation of solar systems and stars. The unpublishable part is something that every astrophysicist should really worry about, and that is the fact that 95% of the content of our universe is dark stuff. We have no obvious idea what it is. And it's called dark matter sometimes, which I think is baloney, because we don't even know that it is matter. We don't even know that it is made of particles. So that's an absolutely essential thing to worry about. But nobody so far has found a good answer to the question, what is that stuff? And I will not voluntarily die before I find out what it is. In my visual arts, I do many different things. Currently, I am building a waterwork for the University of Leiden, in which the water flows in precisely the same way as light flows around a black hole. And relevant perhaps to the discussion today is that I'm also trying to find I'm trying to find a visual response to the question, what would an extraterrestrial galactic spaceship look like?
Okay, thank you very much. So now we thought just to get all of us on the same level as in intellectual wise, first Vincent and then René will give us a short introduction about what is space, what is an exoplanet, what is our solar system, the Milky Way, and just give a short introduction on the intellectual framework of our topic to begin with. So, going in here.
I hope that this is working. No, it is not. I'll just shout, okay?
With a microphone?
No, because it hasn't been sterilized properly. I mean, we're in a strange circumstance. I have no idea. Yes. You will understand that I don't particularly want anything close to my mouth, considering that we're still in the corona circumstances. So, besides which, every now and then this thing drops out. So maybe our technician could take some care of it. Anyway, never mind. I'm going to try and do a brief overview over space, time, and matter. And the reason for this is that these three things, I think, are essential to trying to understand what life in our universe as a whole could possibly be like. To begin with, space. I'm going to do this at top speed, this is to say the speed of light, which is the biggest speed that we could possibly have. Now, a typical planet, this is the planet Jupiter, has a characteristic size of approximately 100,000 kilometers. And if we're going to make this 1,000,000 times bigger, we end up with an entire solar system. And in this particular case, I will show you a small overview over some of the solar systems that have been found outside our own solar system. We call these exosystems, exoplanets, exostars. So that is not our solar system. All these things are real. They have absolutely been verified in our astronomical observations. We know that these solar systems exist. If we're going to make this whole situation 1,000,000 times bigger yet, then we end up with something much bigger, which is our galaxy. A galaxy is a stellar system. In our own galaxy is approximately something of the order of 300 or 400 billion stars, each of which are more or less comparable with our sun. This is an exo-galaxy, but our galaxy would be very similar to this particular view over here. 1,000,000 times bigger yet, we end up with a space scale which encompasses approximately the entire universe. This is the so-called Hubble ultra-deep field, where the typical size and the typical distance is something of the order of 10 billion light years. And if we were to then enlarge that little portion on the bottom right-hand side, we end up with a galaxy in the deep universe, which is not very different from our own galaxy that we have on Earth. So much for space. Now about time. The thing to totally realize when we talk about life in the universe is the exceptionally large quantity of time there is in our universe. We're not accustomed to this. I mean, if you're lucky, you live 100 years. However, if we look at our universe as a whole, we're looking at times that are excessively much bigger than this. The entire age of our universe is 13.8 billion years. This is the glow of the Big Bang that we see in this image over here. Somewhat more recent, the formation of galaxies, 12.5 billion years ago. Something like that would then approximately be similar to our own galaxy. Our own galaxy is 10 billion years old. Our sun would be a star at a distance of approximately 24,000 light years from the center of our galaxy. Our sun and the surrounding solar system, approximately 4.6 billion years ago, our planet Earth, 4.5 billion years old. And again, compare this with our own life expectancy, which is of the order of 100 years, which is as nothing as compared with this. The first chemical evidence of biomolecules on Earth are said, and this is not my research, so I'm just simply quoting people who have studied this, the first evidence for biomolecules on Earth 3.7 billion years ago. Multicellular life, 1.6 billion years, and life that you and I would recognize as more or less reasonable is extremely young compared to the total age of our universe. It all started with the so-called Cambrian explosion only 530 million years ago. The genus Homo grew a branch of 2.5 million years, and our own species, Homo sapiens, approximately 200,000 years. And again, that is thousands times bigger than the longest time any of us could ever hope to live. So let us compare these two. We, as a modern post-glacial species, 50,000 years old, our universe 13.8 billion years, that is a ratio of 300,000 times. Anyway, then the third part is matter. We have had space, we have had time, now about matter in the universe. Matter in the universe is mostly spread in between the stars. There are clouds of gas and dust in between the stars, and this interstellar matter is very relevant to trying to understand how life could possibly have originated on planet Earth. When we look at this interstellar matter, we find that it is composed of atoms and of dust. And a small part of a dust grain in between the stars might look something like this, and on the surface of those dust grains, molecules can form. These are processes that we do know exist. And molecules of this sort that we see on this particular surface here, glycolaldehyde, it's also known as antifreeze, it's the kind of stuff that you have in your car engine. This has been found in great abundance in between the stars. So not even on a planet, but just simply floating between the stars. Let us then look a little bit more about the atomic composition of this stuff. On the left-hand side here, you see another complicated molecule that has been found between the stars. On the right, you see cytosine, which is a part of your own body. It just simply exists inside you. And if you were to look from left to the right, you see that half of that cytosine molecule is already present in between the stars. Now, exoplanets, we have many of them. I'm going to show you just simply particularly one, which is the TRAPPIST-1 system. The planets, 7 planets in this system, behave exactly like it is shown in this computer simulation. And these are 7 planets that revolve around the star in a very orchestrated fashion. Now, biomatter exists on these planets and not just simply on ours. But let me give you a few examples of biomatter that exists on Earth. Right, so we've now specialized from the deep universe to our own planet. Molecules like this, ribose, is part of our own biological makeup. And let me point out to you how this is composed. The white dots here are hydrogen atoms, the red is oxygen, and the bluish green is carbon. Another atom that is very important to life on Earth, of course, is nitrogen, which is green in this particular case. You see that these molecules are very, very simple. Right? They do totally straightforward stuff. It can already get a little bit more complicated when we look at something like this. And most of you on the desk here, I see have already this in front of you, because this is a molecule of caffeine. Now, let us specialize a little bit to the essential atoms and the essential molecules of life on Earth. And I have skipped an enormous distance, of course, and now specializing to just our own planet. Phosphates, deoxyribose, and guanine. Now, if you chain those together, then this is what you get. Let us see where it comes from. Hydrogen comes from the Big Bang, from the initial part of the universe. Carbon is formed inside stars. Nitrogen is also formed in stars, and oxygen is also. The only atom that is a little bit exceptional is phosphorus, which is formed in stars that are very much heavier than our sun. So this thing has been switched. I really haven't the foggiest idea what is happening with your installation here. I'm not switching anything.
Could be the cable. Could be the cable if you drop it.
Staat dit ding helemaal hoog? Weet je?
Yeah.
Probeer het nog eens. Ja.
Okay.
Dit?
Sorry?
Yeah.
Okay. Well, every now and then, the annoying thing is I can shout really loud, right?
It just goes off.
It's the UVA.
So what?
Blame the UVA.
Well, yes, I mean,
Alvaro, will they,
Ja, dat weet ik niet vanwege corona en ons soort dingen.
Alvaro, will it work online if he doesn't use it?
I think we can hear him pretty clearly.
Then without.
can someone solve this for me?
Ja, please. We're trying. Als we zijn even de mijne aan het desinfecteren, denk ik.
So the
I
technician
think
left.
it's the cables.
Ja, maar als we nu de mijne even desinfecteren, dan kunnen we de mijne gewoon.
Yeah. But in the meantime, there's even in the.
Ja, dat hoor.
Okay, so this really, okay. Okay, this under your feet. Okay, okay. Thank you very much. That's very kind of you. So to come back to this, these are all ordinary atoms, right? The only atom here that is to a certain small extent exception is phosphorus, and the rest is totally common. We are looking here at the cheapest stuff that is available in our universe, and out of that cheap stuff, we are made. We are stardust. We're made out of this kind of stuff that just simply floats between the stars. And if you chain this together, then you can see that stacking this together makes complexity. And from now on, I'm basically taking a distance from the astrophysical part of my story. Because so far, everything is common, everything is ordinary, everything is normal. Carbon, nitrogen, oxygen, phosphorus, it's all ordinary stuff. What is not ordinary, as far as we know, is a molecule like this. These are stacks of precisely the same stuff that I have just shown to you, some of which is present in between the stars, floating in outer space. And it is special to a certain extent. This is a DNA molecule. It is a small section, as it were, of a DNA molecule, and it is present in all of us. Somehow, in the past 3.7 billion years, molecules on Earth have succeeded in making this complicated structure. Now, let me be absolutely precise about this. We have no idea how this happened. All right. We can see, however, that it has happened. If you want a little bit more about the astrophysical side of things, I can recommend the book that I wrote about this that you can buy afterwards on the table over here. Let me try and say what I think is the essential summary of the astrophysical story so far. The more we have found out about our universe, the less special we have become. Earth is by far not the only planet in our solar system, and certainly not in our galaxy. There are thousands of billions of planets in our galaxy. Our sun is not special, 300 or 400 billion suns in our galaxy alone. The stuff, the very stuff that we are made of, is totally common. It floats in between the stars, it is present everywhere. There is no reason whatsoever for believing that our galaxy, or our solar system, or our planet, or our atoms are in any way exceptional. And therefore, I will conclude by saying that, at least astrophysically speaking, there is no reason why life in our universe would be exceptional.
Thank you very much for this great explanation. And now I would like to give the floor to René, who will shed some light on the more biological side of this story.
Yeah. So we just learned that biomolecules are everywhere in the universe. There's nothing special about that. But the big trick is, how can you get from biomolecules to something that is alive? What is the step that nature takes from lifeless to living? And nobody understands that. So biochemically, we are very much advanced, and we know exactly from which molecules your body is made. And even when you go down to even a single cell, we cannot create in the lab a single cell. Even if we have a full list of all the biochemical components and we can order them by companies like Merck, when we mix all these ingredients, nothing happens. That has been tried for dozens and dozens of years. It just doesn't happen. And nobody has a clue. The point is, anything that is alive is not just a mixture of biomolecules, it is an organism. An organism means it is organized. All these molecules have a task and they reply to one another. They do as if they are players in a big orchestra. They make one piece of music. And that is still a big dilemma, or let me say a scientific question within the biology. What is the origin of life? How do you make that step, or how does nature make that step between biomolecules and something that is organized into something that lives? Once we have reached that point, simple life, the first evidence of that, as Vincent just told, is from 3.7 billion years ago. Then we have a clue of what happened next. That is Darwinian evolution. Charles Darwin explained how simple life can develop slowly into more complex life until we reach the point that we have today with all these beautiful plants and trees and fish and man, of course. That is explainable, Darwinian evolution. But that first step, where did life come from? We just don't know. We even do not know if that first step was taken on the Earth, because quickly before the first signs of life appeared here, that's 3.7 billion years ago, the Earth was extremely hot and inhospitable for life. Vincent can talk about that much better than I. the Earth first had to cool down to accommodate life. But the strange thing is that nearly as soon as that has happened, life was there. So there are assumptions now that the very first step of life and the creation of life did not even take place here. Life could have been imported from another place in the universe with completely different circumstances that are beneficial or even required to make life from non-life. Anyway, I do not want to end my story too pessimistic. There are many questions that need to be resolved, and I hope that will be done in the coming years. I'm really looking forward to the answers.
Okay, thank you very much. So you keep talking about the first signs of life, when life started, but what actually is life? How do we define what is life?
Well, we have only one example of life, and that's life on Earth. There is no other example. There was never life detected
But what is
anywhere else.
life? Is it,
So we can only extrapolate that. So we can say we have a good idea of the molecules, the biomolecules. We know that living organisms can reproduce themselves. That is a specific feature of life. They can grow, they can develop, they have a metabolism. That means there's an uptake of molecules from outside, and they are adapted or changed or transferred into something that can be used in that living system. Metabolism. And also very special for life on Earth is the genetic code laid down in DNA. But the only assumptions that we can make are based on life as we know it here on Earth. Perhaps there is another type of life possible elsewhere in the universe. We have no clue about that. It may look completely different and be composed of different molecules, and even the genetic code is not. There's no strict need to lay it down in the DNA. Perhaps there are other molecules that can fulfill that same task.
Okay, but then if we are searching for extraterrestrial life, or we're screening for it, do we then define life on Earth in the same way as extraterrestrial life?
For the moment, yes, because there is no other starting point.
Okay, but also then are we assuming that what's necessary for life on Earth, that's what's necessary for extraterrestrial life?
Yes, yeah, but that is still, it is an assumption, but it is a good assumption. We have to start somewhere with our search.
Yes, definitely. But So are we looking just at molecules, or do we want to find cells or multiple cell organisms?
No, the best is to look for living stuff. To send robots to other celestial bodies and to look if there is something really alive there. But that's technically extremely complex. And even the new landers, which are on the way to Mars, are not equipped to detect living systems. They're only looking for biosignatures.
But in this sentence, what do you mean with living? Like, is it
That it is growing, reproducing, breathing, or photosynthesizing.
Do you agree, Vincent? Is that what defines life?
I think it is a mistake to ask for definitions. We are physical scientists, and physical sciences never stop because we will never, ever, ever know everything. You can only define something when you know everything about it. So that is why mathematicians define things, okay? Because they live in their own universe. If a mathematician has invented something, it exists because it has been defined, right? Life is not something that we can define. No more. If you ask me what is the definition of a planet, what is the definition of a star, you give me your definition, and I guarantee you that I can find a sensible exception to that definition. So, and the reason that I think I should emphasize that asking for a definition is the wrong way to go is that, and I sort of heard that a little bit in what René was saying a moment ago, that people might think that there is a single step between non-life and life. Once we have taken that step, we're there, we're home. There's no such thing. It is, those of you who have seen the film Contact, which is about extraterrestrial life and things, will have seen this. Small steps, Ellie, small steps. And that is the essence of the evolutionary process that Darwin and Wallace have discovered. Many, many, many very small steps. And nowhere in that enormous string of steps can you say, aha, step billion so-and-so and is no life, and step billion so-and-so plus one, we have life. Right? And that is another reason why deep time is so very, very important. And to try to frame your mind into a frame where you go back 10 billion years and not just simply a few years.
Okay, but then still my question remains is that if we were screening for life, like we're actively looking and screening for extraterrestrial life, what are the specific parameters or variables that we are kind of checking on? For example, is it oxygen, is it hydrogen? Like, what are the specific variables that we're screening on if we're actively looking for extraterrestrial life on other planets?
Well, René's answer we just picked up, right? I mean, if you, as a biologist that you are and stuff, you look for different processes that we in astronomy look for. The typical state of research at present is looking for occultations. That is to say, you have a star and you have a solar system around that star. Every now and then, it may just happen that the planet is in front of the star. And then the light from the star passes through the atmosphere of that planet. And that means that we can, as it were, on Earth, detect what the chemical and physical situation is of that atmosphere. At present, that particular part of research is still in its infancy, but currently we are developing, not me because I'm not an engineer, but my very, very clever engineering friends are designing pieces of equipment that will allow us to find chemical signatures of what is going on in those atmospheres. From there to detecting life is, of course, a big step. However, looking for complicated, non-equilibrium chemical processes is going to be our first step, trying to find out what's going on there.
And that's what happened last week with Venus, right? Or last week. Last week it was published, and it was world news that the atmosphere of Venus contained phosphine.
Oh, phosphine, yeah, on Venus. Well, I'm very skeptical about this. I know from experience that if you want to impress people at large in astronomy, there's three ways in which you can do it. One is you can talk about the Big Bang, two is you can talk about black holes, and three is you can talk about life in the universe. Right? So as soon as people's research shows that something that they might try and advertise in the media as a signature of life. They jump to the occasion. I think that is going very much to phosphine, is a very simple, straightforward molecule that apparently occurs in the atmosphere of a planet, of which I think René would say the probability of life on Venus is minuscule. Let me point out the fact that Venus is so hot that on the surface of Venus, lead would melt. Now, I think it is totally improbable that there is life there.
Yeah, it's not in the habitable zone, as we call it. No. First, a remark about the intermediate steps from between non-life and life. On Earth, we cannot find these, but they may have been consumed by our current animals. Look, it may be a broth full of proteins and I don't know what delicious components, but then these intermediate steps may have been there, but they are no longer here because they have been taken up by the living organisms, as we talk about now. Now, more about the direction of the press. There are signs of extraterrestrial life. That has also developed step by step, because 25 years ago, newspapers were not telling anything about the possibility of extraterrestrial life. And now, if somebody is speaking about the possibility of life on Mars, everybody gets excited and everybody has fun, but nobody is concerned and nobody says that is a big fool, that is nonsense, that is science fiction in the worst meaning. No, life on Mars, that is now a common piece of information. Nobody is any more surprised about that. So I think that is an interesting development.
But isn't it the fact that people aren't scared of this type of life is the difference between life as you all say it and intelligent life? Because I think that would be a scary component.
Yeah. And that is also, you can also see that in the newspapers again. Because if you talk about life elsewhere in the universe, the common opinion is, yes, the universe is that large, it is so extremely large that there should be life anywhere else. No question about that. But what you never read is there should also be life that is much more advanced than our life. And so there should be creatures around which are much more intelligent with a much higher technology than we have. But that is the consequence. If you take step one, you say, yes, there is extraterrestrial life because the universe is extremely big. And then the following step is, in that case, there's also life that is much more advanced than ours, because our planet is not a typical example. There are solar systems which are much older than ours. And our technology has only developed in the last 100 to 200 years. There should be civilizations which are much more advanced than ours. But that is not part of the common opinion nowadays. That is still risky, or I don't know, or scary.
Yeah, well, I'm very happy that you were talking about starting up technology, because my question is now, how actually do we screen for life? So what are technologies, how do we, the technology behind the screening for life?
Well, there are different methods. You can look at radio signals. That has been a project that has been running also for dozens of years, called SETI. And so far, there is not a solid result obtained. So scanners are looking in the universe to find radio signals that could be connected to intelligent life, special patterns.
And is ESA doing that as well? So you work at Aztec?
No. ESA is not involved in that. No.
So what kind of projects
It is
do they
an
have?
American project mostly.
Oh, right. But does the ESA have any projects?
No. Yes. Yeah. Now you're talking about the search for life in general. Yes, surely. What we have been doing is to conduct biological exposure experiments. So what does that mean? Life on Earth is extremely diverse. And we know that most of life cannot survive in open space. In open space, there is vacuum, there is solar UV, there are cosmic rays, there are wide temperature fluctuations, plus 30, minus 30, that is not acceptable. and there is weightlessness. And we have tested the behavior of terrestrial organisms to these weird extraterrestrial conditions. I've brought an instrument with me in my bag. I will show it to the camera. Come on. Is that visible? Yeah?
Yeah,
It's big enough, yes.
Yeah? Yeah? Okay. We started our experiments.
This is camera.
Yeah? With. Yeah?
Right there.
Yeah?
You got it.
Yeah? Okay. We started our experiments in 1990 with this container.
One step back, so the camera can get closer to your face.
Yeah? Yeah? Okay. It was made in Russia. It's called the KNA. Container naočnoj aparatury. And it is so simple, it's unbelievable simple. You can put anything you like in this pan. Yeah. That pan is screwed on top of a satellite. Satellite is launched, lid is opened, and everything that is inside is exposed to these weird conditions in space. Vacuum, solar UV, cosmic radiation, weightlessness, wildly moving temperature changes. At the end of the flight, the lid's closed, the satellite comes back to Earth, and then you can check what has happened to your test materials. And you compare it with a ground reference, of course, exactly the same stuff which has not seen space. And in that way, we discovered that even simple plant seeds like even simple plant seeds like lettuce seeds, they can survive for more than 1.5 years in space without suffering any damage. And the same is true for some lichens. You know what lichens is? Cosmos lichens. Even some small animals, tardigrades, they can survive the trip. And some archaea too. And that was completely unknown. And that is important because it could mean that a life, simple life, could be transported from one celestial body to another in the same solar system by meteorites, for instance. They could be a passenger on meteorites. That means that we have a new clue to the distribution of life, at least within one solar system. It is possible in nature that life makes a transit from one celestial body to another one, because they can survive that trip. It's not true of all the terrestrial organisms. We will immediately die without a spacesuit, and the same is true for a normal plant. But organisms in a dormant stage, several of them, are capable to survive such a trip. So we found many new results because nobody knew about that. And there is also not a biological clue why are some terrestrial organisms adapted to cope with that weird trip. We just don't know. But it is also important for what's called planetary protection. It means that everything that we send to another planet should be fully sterilized, because some of our organisms are extremely robust.
Okay, we have a question from the audience.
Yeah.
So we know that life can survive the trip and
Yeah.
even the landing to a new planet.
Yeah.
What about the initial blast that would put that meteorite into orbit? Or like just the planet exploding? Or the origin of
Well,
the
shock
meteorite?
tests have been performed.
Exactly, yeah.
And the smaller the organisms, they better they are resistant against shocks. Yeah, that has been simulated. Yeah.
Perhaps I should sort of cut into this. There are meteorites that have been found on Earth, in particular on the South Pole, of which we know that originally they were part of the planet Mars.
Yeah.
They exist. I mean, from the chemical composition and things, we know that there's pieces of Mars that have ended up on Earth, and almost certainly vice versa. Another remark, my colleague Simon Portegie-Zwart at Leiden University has found that there are even what you call non-solar system planets. There are planets moving around in space that aren't even part of a solar system, they just travel around. Currently, there are 2 objects that have been found in our solar system, passing through our solar system, of which we are absolutely certain that they came from outer space and did not originally form part of our solar system. So these visitors from out there do in fact pass through our solar system. We know they exist.
And we have another question from the audience.
Yeah, so I was wondering.
Hey, speak a little louder.
Yeah, I'll try to speak as loud as possible, but I was wondering because if an organism can survive that traveling through space, doesn't that make the finding of Venus a little bit more interesting because it's known that we have organisms on Earth that can survive at least like 300, 400 degrees Celsius when you're talking about the organisms that we live near thermal vents. So Venus, I don't think it's much hotter than that, is it? I think it's about 500. So doesn't that make that a somewhat more interesting
Okay, so
observation?
try to repeat the question a little bit louder. So what you're saying is if there's organisms living on Earth right now that can still live in temperatures above 30,000 Celsius, so doesn't that make the finding on Venus more interesting? Because if there's living organisms here that can survive such heat, why shouldn't it, that's even cooler, but it is found on Venus?
The problem is that it's difficult to imagine how life can survive on.
Nee, even met de microfoon.
Ik doe het niet goed.
Je moet hem echt zo.
Heel dichtbij. Okay. As they said previously in the former Soviet Union, would you please talk directly into the flower pot, please?
Yes, so far that has not yet been investigated, the possibility about transfer of light between Venus and the Earth, and the Earth and Venus. But yes, if it turns out that there is really a specific type of life possible on Venus, which is doubtful, then it would be interesting to look into that theme. Yes, yeah.
Okay, so now I kind of want to go back to the start of research into extraterrestrial life. Why exactly are we, like, you have NASA, you have the European Space Agency, so much billions of euros and go towards this investigation, but why do we actually research this? Is it geopolitical? Is it because of climate change? Is it just because of pure interests? Why are we researching this?
Now you're talking about the biology that takes place under the umbrella of ESA, of the European Space Agency.
Just in general, why are we all researching?
It is mostly out of scientific interest. We want to have answers to questions that have been along for I don't know how long. For instance, the start of life, and are we alone in the universe? That is a question that was raised ages and ages ago. And the possibility of life on another planet, that was already coined by Christian Huygens, 17th century. There's nothing new about that, but now we have entered an era with technologies that allow us to test all these predictions and theories and ideas.
So, do you have a question from the audience?
Yeah,
Yes,
I just
that
relates to this.
we have a question from the live stream.
So since you can send with this thing, you can send earthly life into space.
Yeah.
Have there been experiments that do this to exposing other planets to earthly life, and how did that go?
Well, that pen that I showed you, that was a precursor of a much better pen. This one was made in Russia that I just showed you. There was a better one made by ESA, with much more sensors on board. It's called BioPen. That has been followed up by an even more complex machine. It was called Expose. And we were able to simulate the Martian conditions also in these instruments. We used experiment containers with a glass on top made of magnesium fluoride. That means it is fully transparent to solar UV, down to 110 nanometers. And that was filled with a reproduction of Martian air. And also the solar spectrum that exists on Mars was replicated in that way. And we have beautiful results from these Mars simulating experiments. And again, it appeared that several terrestrial organisms can survive under Martian conditions. I do not want to say that they could grow, develop, and breathe, these were dormant organisms. They were asleep, so to say. But they could survive under these conditions for a pretty long time.
Didn't the Chinese send grow something on the moon?
Yes, yeah, plants, yeah, but they died after 2 weeks. And that is, but the plants were not growing in the open air. They were in an incubator. So you can put that incubator anywhere in space. But the temperature control was not that rigid that the large temperature fluctuations on the moon could be countered. So at a certain moment, it was getting too cold and everything froze up.
Is it still an interesting fun, you would say, or just a show?
It was more, yes, it was more a technology demonstration than a solid scientific experiment.
Vincent, do you want to talk?
Well, yes, I mean, to come back to the original question, why do we search for life? I think the fair answer is we don't. In astronomy and astrophysics, the search for life is a very, very small specialty subject. However, it makes headlines and it pays the bills. So that is why it's something that can sort of give you the headlines and things like that. As already pointed out in my personal introduction, 95% of our universe is dark stuff of which we have no idea what it is. That is what we're after. Okay, so the key questions in astrophysics and in astronomy are not really related to light. Besides which, in the physical sciences, we typically take very small steps. And our famous colleague, Professor Evine van Dishoek, who is perhaps the most famous astronomer on the planet, she and her research group are studying interstellar molecules, cosmochemistry. And it is from that cosmochemistry that Van Dishoek and her co-workers are assembling step by step by step an understanding of what molecules do in interstellar space and what molecules do in stars and planetary systems that are forming. There is a special telescope, the Arnold telescope, that has been built in South America and Chile, in part in order to study this particular subject. But everybody would agree that we are a long way away from the subject that René is talking about. Right? There's so many steps in between. We're just simply not doing that. And in particular, when we ask ourselves, and you said this just a moment ago, what about intelligent life? From a biological point of view, we ought to realize that intelligence is an extremely important asset in the struggle for existence. If you have an organism that understands the relationship between cause and effect, which is, intelligence, then you survive much better than another organism that does not. Intelligence on this planet is very, very, very widespread. There are thousands and thousands of different species on this planet that are intelligent. And we, again, I said in the beginning of my discussion that we are not exceptional. And also in this respect, we are not exceptional. I mean, intelligence is so important. There are many species that have it. And for the rest of the universe, we can say something similar. Almost certainly, if there is life outside Earth, and if there's evolved life outside Earth in our universe, there must be intelligent life, because biologically speaking, intelligence is so fantastically important. If I may, just one small remark about let us not be too modest, let us not be too parochial. I have already shown to you this double helix of DNA, okay, that René sort of also talked about, and that we're very familiar with. Let's skip. René has been explaining to us that traveling through interstellar space is dangerous because the ultraviolet radiation from the stars, because of the cosmic radiation of particles that are hitting you. Now let us just simply imagine that there is a form of life in the universe that does not have a double helix, but a triple helix. In our DNA, a double helix cannot really correct itself, because if there is an error, which one of the two parts of the helix is going to be right and which is wrong? You don't know that. But if you have a triple helix, then an error correction system is possible that just simply by majority vote says if you have AAB, then the B must be wrong, we'll change that into an A. And we know this exists. Keratin is a molecule that you have in your head. Your hair is made of keratin. That's a triple helix. So the triple helix already exists on Earth in our own bodies, except we do not use it as a genetic molecule. If you have an extraterrestrial species that is based on a triple helix. They might travel through space and correct the space damage even better than what you were discussing a moment ago. And just for those of you who are interested in writing science fiction books, right? If you have a triple helix, you must have a triple genome. If you have a triple genome, you have 3 parents instead of 2. And just let us imagine what literature you could write if you have 3 parents instead of 2.
Well, that's very interesting. Were you familiar with that?
No,
name?
no, that's new to me.
Oh, but that's very interesting stuff.
You want to add something?
No, please continue.
So you were mentioning that statistically life isn't that unlikely in the universe, but that brings us to the Fermi paradox. It's like this statement or paradox that says that statistically there should be life, like because there are so many planets out there with the possibility of life. Then why haven't we found it yet, or why haven't they found us yet? So have you any thoughts on that?
Yes. Oh no.
Well, there are 2 simple reasons why we have not yet discovered extraterrestrial life. One is that we are too stupid to find it. The second possibility is they are too smart to make themselves found. So either of those 2, or maybe it doesn't exist, which is, in my opinion, improbable.
Do you agree with
Now
that?
there
René?
is a third possibility. They are there. UFOs. Yeah, that is never discussed in any scientific talk. But that, in the United States in July, they made already a change. Now they confirm that the UFO observations by the US Navy are real. That means you do not have to believe in UFOs. The UFOs are there. Only what is it? Nobody knows. But the way UFOs behave in comparison to what we know about aircraft and rockets, it's completely different. And it is, you cannot understand how they move into the air, in and out. They disappear, they stand still, move up at a tremendous speed. And now that phenomenon, these observations have been confirmed. So these strange objects are there. And to avoid a confusion with UFO, because UFO, everybody is thinking about science fiction and weird movies and comic books, they changed the name to Unidentified Aerial Phenomenon, UAP. So if you want to talk as a scientist about something which is really serious, about UFOs, nowadays you have to talk about a UAP. This is to avoid confusion with fantasy stories. Yep. And so the observations are there. Nobody knows what it is. Nobody knows how it works. But it could be a phenomenon that is related to an extraterrestrial intelligence or an extraterrestrial technology. I cannot say anything more about that because nobody understands what it is. But the starting point is there to take the observations seriously.
All right, thank you. Vincent.
I think that is total bosh. I mean, if I have an experiment for you, okay, wait until it's dark and you're in your bed, close your eyes and try to identify every sound that you hear. I guarantee you that 15% of the sounds that you're hearing is something that you cannot identify. That doesn't mean that there's extraterrestrial in your bedroom.
No. Because nobody knows what it is. There is a possibility that the origin is extraterrestrial, but not necessarily so.
There's equal possibility, and some on our planet would say that the possibility is bigger, that there is a spirit from God, that is in your bedroom or something like that. I think this is it. No, we cannot take this seriously in any way at all. When you say unidentified, okay, fair enough. Let's scrap that and go and do real science.
Okay, well, I think we're almost running out of time. So if there's any questions from the audience or online, then I think we unfortunately have to end this super interesting talk. I first want to give a round of applause to both of our speakers, so thank you very much.